Imagine you're a kid in elementary school. You've just been taught what a fraction is, and now you're about to learn how to add them. For many kids, the most natural thing to do would just be to add the numbers across. Obviously, this is wrong. You're doing something to the fractions here, but it certainly isn't adding them. What is this even doing to the fractions? Is it useful? Is it even coherent? It turns out this is actually a thing, and it's called a mediant. The mediant of these two fractions is obtained by just adding the numerators and adding the denominators. However, usually when people work with mediants, they add two particular conditions. The first condition is that our fractions are rational values, so no irrational numbers are allowed. And the second condition is that our fraction is in simplest form. To see why we add these conditions, consider the following example. The mediant of these two fractions gives us this. Notice that since 1/2 is equal to 2/4, we can substitute that. Since we didn't change the input fractions, we should get the exact same mediant value, and as we can see, we do not. This violates our intuition, because the same two values can result in a mediant that can literally be any real number. How can we even do math with this? How would this even be useful or coherent? This is why we want our fraction to be standardized, such that there is precisely one way that the value can be expressed, which means that there is precisely one possible value for the mediant. And so we declare that our fractions must be in simplified form, which is only meaningful if the value is rational. Okay, cool. Now we have a well-defined operation called a mediant. Now what? What can be done with this? Let me first give a seemingly unrelated scenario, and then let's talk about how mediants are related to it. Imagine on this table I have two buckets. This bucket has 5 black balls and 6 white balls, and this bucket has 3 black balls and 4 white balls. You want a black ball, but you can only pull one ball at random from either the first bucket or the second bucket. Which bucket should you choose? You should choose the bucket with a higher proportion of black balls. In the first bucket, there is a 5 out of 11 chance of pulling a black ball, and in the second bucket, there's a 3 out of 7 chance of pulling a black ball. 5/11ths is bigger than 3/7ths, so you should pick the first bucket. Simple. What about these two buckets? In the same way, we can see that the first bucket gives us a higher chance of pulling a black ball, so we should once again choose the first bucket. Okay, here are all 4 buckets. Let's combine the buckets we wanted to choose, and let's combine the buckets we didn't want to choose. Which combined bucket should we pick now if we want a black ball? If you count carefully, you'll notice that it is actually better to select the bucket combined from the ones we didn't want. This is known as Simpson's paradox. It is a paradox in the loosest sense, in that there is nothing contradictory, there is nothing wrong with the problem statement, and there is no trick. It's just unintuitive, that's all. Now let's take a look at how we can use medians to make this much more intuitive. When we write a fraction y over x, oftentimes we think of representing it on the number line, based on the value of y divided by x. Since we require both x and y to be integers and fully simplified, we have a unique representation of each rational value. Instead of placing it on the number line though, let's create a representation more directly relating to the x and y values we chose. Let's use vectors. For instance, the fraction 2/3 we will represent as the vector 3, 2. If you're wondering why I used y over x instead of x over y, that's because the value y over x now represents something useful and familiar to us with respect to the vector. The y value is the rise and the x value is the run, so y over x is the slope of our vector. Basically, we can represent these fractions as the slopes of these vectors. Before, we assign a fraction to each bucket that represents the probability of drawing a black ball. Now, we will instead assign each bucket a vector w, b, where w is the number of white balls and b is the number of black balls. The slope of the vector represents how likely a black ball is pulled. The higher the slope, the more likely. We can model both of our buckets with vectors to see which bucket we should choose. In this way, combining two buckets would be like adding two vectors together. Adding the number of black balls together is the same as adding the y components, and adding the white balls together is the same as adding the x components together. If we examine the slope of the sum of the vectors, this is how we get our mediant, and how we get a very natural understanding of what a mediant is doing. Now let's use this representation to reinterpret Simpson's paradox. What Simpson's paradox is saying, using the language of our vectors instead of the language of probability, is this. Suppose you have two pairs of vectors. Add the vectors of higher slope together and add the vectors of lower slope together. It's possible that the slope of the vectors made up of lower slopes is higher than the slope of the vectors made up of the higher slopes. There are a lot of ways in which this could happen graphically, and so hopefully Simpson's paradox shouldn't feel so unintuitive anymore. So that was a practical example of how mediants can teach us something. Well, kind of. It's not that just inventing a new math thing on its own taught us anything. It's how we understood its properties and how that can be translated or applied to other problems. Now that we have seen one particular practical example of how mediants can teach us something, let's take a look at a fancier problem. Suppose I start with the two fractions 0 over 1 and 1 over 0. Yes, 1 over 0 is undefined, but remember these fractions can be represented as vectors. So let's say that 1 over 0 is allowed in the same way that 0, 1 is a valid vector. 1 over 0 simply refers to the slope of the 0, 1 vector, a vertical direction. Now let's take the mediant of these two fractions, 1 over 1, and stick it between them. Now we have three fractions. Let's continue to take the mediant between adjacent fractions, sticking them in between. If we continue this process to infinity, we will eventually list every single positive rational number exactly once, in fully simplified form, and in order from least to greatest. Impressed? Let's prove these claims. Let's begin by proving some basic concepts that we will be using a lot throughout this video. The first one is the idea that the mediant of two fractions will always be strictly between them. To see why this is true, let's take our fractions and convert them to vector representation like we did before, and compare the slopes, which is the value of the fractions. Notice that no matter how you add the two vectors, the slope of the sum is always strictly in between. Note that this particular inequality holds true not only for rational values, but any fractions whatsoever, even if the fraction is not in simplest form or irrational. Next, we should understand that for two fractions a over b and c over d, the area of this parallelogram that we created here from the fractions vector representations is AD minus BC. First, we draw a rectangle of area AD. We can cut and move these shapes around without changing the overall area. By sliding these triangles up here and then subtracting out this rectangle, which includes some overlap, we have the parallelogram. Another fact we need is that the area of the parallelogram can also be understood as the length of the base times the length of the height, which means that no matter how we shear the parallelogram like this, the area doesn't change. Okay, here's where the fun begins. Take any two fractions such that AD minus BC equals 1, or in other words, the area of the parallelogram made by the vectors is 1. If we take the mediant of these two fractions and find the areas of the parallelograms made with the original vectors, each of them also have an area of 1. The reason for this is quite simple if you remember that shearing a parallelogram like this doesn't change its area, and the area of this parallelogram is 1. However, you do have to be careful as there is another important detail to this reasoning. Notice that this shearing argument never makes use of the fact that AD minus BC equals 1. If we try the same argument with the mediant of these two fractions, we can say that by shearing, we preserve the area, right? When we write out the fractions, we get that the mediant is 3 over 3, which must be simplified to 1 over 1. This shrinks the parallelogram formed with this mediant, so the area is not in fact preserved. That's why AD minus BC equals 1 is an important detail. When calculating the mediant, it does not need to be simplified, and so the mediant vector won't shrink, preserving area. But why is the mediant in simplest form in the case that AD minus BC equals 1? Not being in simplest form simply means that there is no common factor in the numerator and denominator. Notice that if AD minus BC equals 1, No matter what integers these variables are, there are no common factors between a and b, a and c, d and c, or d and b. To see why, let's pretend that there is a common factor between a and b. We will call this common factor k. That means that we can factor out k, and we get that an integer times an integer equals 1, where one of these integers is bigger than 1. This is impossible, so there cannot be any common factors. We can use the same argument for any of the other pairs. So now let's examine the mediant of these two fractions. If we substitute these values into this AD minus BC expression, then simplify, we will notice that we obtain AD minus BC again. Assuming that AD minus BC equals 1, this expression is also equal to 1, which proves that A plus C and B plus D have no common factors, meaning the mediant is fully simplified. Another fun but important fact. Imagine you have two fractions such that AD minus BC equals 1. There are an infinite number of fractions between them. The mediant of the two fractions is not only in simplest form, but of all of the fractions in between, it is a fraction with the lowest denominator. Let's prove this. There is a unique linear transformation that turns the unit vectors into the vectors of our two fractions. This will also transform all other vectors as well. Let's suppose that we start with the vector 2, 1 and apply this transform. Where does it land? The vector 2, 1 tells us that we want to add 2 of the x unit vectors and 1 of the y unit vectors. While the unit vectors are transformed, it doesn't change how they are added, and so this is how we get our transformed vector. Notice that the vector 1, 1 is transformed into our mediant, the sum of the vectors. Since we are looking for the fraction with the smallest denominator, and the denominator is represented by the x component, we want the vector furthest to the left after transformation. This is our transformed 1, 1 vector. If either of these components are increased, we move further to the right. This is the smallest we can make our vector components, so it is the smallest denominator. Well, once again, we have a small detail to this proof that needs to be addressed. Why couldn't a non-integer vector transform into a point that we missed? We show that a complete set of the lattice points in the first quadrant will be transformed into a set of lattice points that lie between the fraction vectors. Now we will show the converse, that the complete set of lattice points between the fraction vectors will be reverse transformed into lattice points in the first quadrant. Let's begin with a vector with integer components. It doesn't even have to be the lowest denominator, just any vector. First, we look at the parallelogram made with this vector and this fraction vector. Now, we reverse the transformation. Since AD minus BC equals 1, and this happens to be the determinant of the transformation, area is preserved. Whatever the area of the parallelogram is, it will be the same before and after the transformation. After reversing the transformation, we see that the area of the parallelogram is simply 1 times y, or just y. The area of the parallelogram before reversing the transformation was an integer, and this is equal to y, which means y is an integer. The same argument can be used on the other side to show that x is an integer too. So now we can see that reversing the transformation must give us an integer vector. Thus, the transformation gives us a complete set of all of the lattice points between the fractions. Did you notice that a lot of these facts depend on AD minus BC being equal to 1? This seems like a very specific condition, and it is. But fortunately, when we start with the 0 over 1 and 1 over 0 fractions, they satisfy this property, and we know that any time we take a mediant of two fractions satisfying this property, the mediant also has this property with the fractions next to it, which means that no matter how we take successive mediants, AD minus BC is always equal to 1. Very convenient. Finally, let's put it all together to show that when we take successive mediants, every possible positive rational number occurs exactly once in fully simplified form in order. Let's first show that no rational number occurs more than once. This is simple. because the median slope is always strictly between the fraction slopes. Now let's show that every rational number appears in this sequence. Suppose there is in fact a rational number that is missed. Well, it is definitely between two other fractions, and if you just take the mediant of those fractions repeatedly, you are guaranteed to find it, since the mediant is always of the smallest denominator. Therefore, it's not possible to miss anything. And there we have it. We have rigorously proved that successively taking these mediants will always lead us to a complete list of positive rational numbers in simplest form, combining concepts from number theory, geometry, and linear algebra. The Farey sequences are the sequences of fully simplified rational numbers between 0 and 1 that have a maximum denominator. We can see that by producing all of the rational numbers in this way, we can eventually get any Farey sequence we want by filtering out some of these fractions. It should be noted that all consecutive fractions in any Farey sequence of any order also satisfies the property of AD minus BC equals 1. See if you can prove this. The tree structure produced from the medians is called the Stern-Brocot tree. Every time we take successive medians, we get the next layer of the tree. Cool! We learn about Farey sequences in the Stern-Brocot tree and some of their properties. Now let's do some fun stuff with them. Let's create the Stern-Brocot tree, but this time using our vector representation. At each layer, we take the medians of the fractions, which is the same as taking the sum of the vectors. Each of these lines points to a lattice point that we can see from the origin that is not blocked by other points. Eventually, every single point that can be seen from the origin will be drawn. Aside from just being cool looking, this visualization helps us see that fully simplified rational numbers correspond to lattice points visible from the origin, and the mediant operation helps us list all of them. Let's look at something related. Here I have the real number line, focused on the segment between 0 and 1. At each rational number on this number line, we will draw a circle above the line, touching it, with a radius equal to 1 over 2d squared, where d is the denominator of the rational number when fully simplified. These are called Ford circles, and they never overlap, and in fact many of them are tangent to each other, as you can see in the figure. In fact, any time two fractions satisfy AD minus BC equals 1, the Ford circles corresponding to the two fractions will be tangent to each other. The converse is also true. Anytime two Ford circles are tangent to each other, it means the fractions satisfy AD minus BC equals 1. The proof for this involves using mediants, and it isn't too difficult to work out. Due to time constraints, I won't be going over the proof in this video, but leave a comment if you would like to see a proof. What makes this visualization so interesting is that now we can precisely visually see all of the pairs of rational numbers for which our AD minus BC equals 1 condition is true. We can now also intuitively understand some other facts from this, such as the idea that for any rational number x, there are infinitely many rational numbers you can pair with x, such that AD minus BC equals 1, because there are an infinite number of circles tangent to any circle. Finally, let's talk about an amusing result in rational approximations. Numbers like square root of 2 are known to be irrational, meaning they cannot be represented as a rational number. However, there are plenty of rational numbers that are pretty close to its value. For instance, look at this sequence of rational numbers. We get the next fraction by incorporating the next decimal place, and as this sequence goes on, we get closer and closer to the true value. The larger the denominator, the closer you can approximate it, or in other words, the smaller the difference between the actual value and its rational approximation. Now, take a look at this sequence of rational numbers. Notice that even though the denominators are much smaller, they are much more accurate. But the question is, how close can a fraction get to an irrational number? The best possible result is given by this statement here. This result is also known as Hurwitz's theorem. This inequality might look a little intimidating, so let's break it down to figure out what it's saying. First, we select an irrational number. Let's choose square root of 2 like before. Now let's test whether a rational number satisfies this inequality. The left side is the distance between the irrational number and the rational number. we plug the denominator into the right side. Notice that this satisfies our inequality, so 3/2 works. Let's try another fraction. Let's plug in 10/7. Even though this rational number is much closer to square root 2, it is not considered close enough to satisfy this inequality. Given the size of the denominator, the inequality desires the value to be closer to the irrational number. Hurwitz's theorem says that no matter what irrational number you select, there will always be an infinite number of rational numbers satisfying this inequality, which means that you can always get arbitrarily close to the irrational number using the rational numbers that satisfy this inequality. To see how this relates to our mediants, we will need to first look at how this relates to the Ford circles. Notice that once we select a rational number p/q, the right side of the equation tells us how far away the irrational number must be in order to satisfy the inequality. Suppose we select 3/2 as p/q. Then we get this to be our distance, and we can see that the irrational number must lie in this interval. Another way to visualize this is using our Ford circles. If we draw our Ford circle, the radius is 1/2q squared. To get 1/5q squared, we just rotate our radius until we get a triangle such that the height is half the width. This gives us a shape where the width on each side is the 1/q squared that we want. This shows us that the desired interval width is proportional to the radius of the Ford circle. Let's call this width the Hurwitz range of the circle, just for convenience. Now let's take a look at these three general circles, tangent to the bottom line and each other as shown. These look like Ford circles based on how they are tangent to each other, but unlike Ford circles, we aren't attaching any rational numbers to them. They are simply arbitrary circles. Notice that we can adjust the size of the right circle relative to the left circle in a continuous fashion such that tangency is maintained. Now on the bottom white line, we will make a couple of markings. If we mark where the left and right circles are tangent, then we can see that the Hurwitz ranges of all three circles seem to cover the entire line. In other words, there is no way we can select a point on the white line that can somehow dodge all three of these Hurwitz ranges. And this is true no matter what the relative sizes of the left and right circles are. To see why, let's draw vertical lines at each of the three tangent points. Notice that there is a boundary condition where the two Hurwitz ranges just barely touch the third one, and this is also where two of these vertical lines meet. Next, remember that we constructed the Hurwitz range by creating these triangles. Finally, we will connect the centers of the circles to make these two lines. Watch what happens when the right circle becomes larger. This guideline connecting the centers of these circles now overlaps the triangles, which means the corresponding Hurwitz ranges do not overlap. The other line misses the triangles, which causes the Hurwitz ranges to overlap. If the right circle becomes smaller rather than larger, the line that overlapped the triangles now misses, and the line that missed the triangles now overlaps with them. No matter what size we select our right circle, we will always have two of these Hurwitz ranges overlap. Well, as long as we are ignoring the boundary case anyways. It turns out that the ratios of the radii is the square of the golden ratio. This number is irrational, and our Ford circles were constructed using rational numbers, so this exact boundary case can never happen anyway. In this particular explanation, we skipped over some details, such as why the ratio is the golden ratio squared, but these are generally derived by relatively straightforward but possibly tedious algebra and geometry. So once again, I won't be going over the proofs, but leave a comment if you would like to see something anyways. Feel free to leave a comment if you have any interesting insights. I also have a Desmos link in the description if you would like to play with this figure yourself. Alright, let's get back to why we did all of this in the first place. Through this demonstration, we can now show that for any two tangent Ford circles and the mediant Ford circle, every real number between the two Ford circles must land in the Hurwitz range of at least one of the three circles. Now notice that for any irrational number we choose, there are an infinite number of pairs of tangent Ford circles that surround it. This corresponds to an infinite number of fractions that satisfy the inequality, and this proves Hurwitz's theorem. Not only that, this intuition provides the foundation to finding a simple, fast procedure to finding all of the fractions for any given irrational number. If the concepts demonstrated in this video are understood, then this should be an interesting programming challenge for anyone who is interested. Can you use these ideas to find all of the best rational approximations for pi? We are now closing in on the end of the video, so let's take a minute to reflect on our journey. First, we talked about how fractions can be added incorrectly. Then we examined that process and wondered, even if it isn't how we add fractions, is it still a meaningful operation? We had to then tweak our domain slightly in order for the mediant operation to be well defined, but this allowed us to determine many properties of this operation and a way to visualize it. This made it very easy for us to understand Simpson's paradox. Then we took a look at a structure we could produce using these mediants, specifically the Stern-Brocot tree and Farey sequences. We used principles in geometry, linear algebra, and number theory to prove some of the properties of these structures. Even making fun extra visuals. And these properties gave rise to another visualization, Ford circles. Finally, we used the Ford circles to help visually prove Hurwitz's theorem, an important result in the study of rational approximations. If it seems like this winding path of mathematical ideas didn't particularly have a specific direction or goal, then in one sense you'd be right, and that's sort of the point. Mathematical ideas aren't always well structured like a school course, where we go from topic to topic within a particular subject. From where we started, we didn't really have any idea where the mediant concept would lead us, but we ended up with useful and valuable insights anyways. One way that many people approach math is by learning whatever one feels is important, the things that are the most applicable and the most useful. We did demonstrate the practical value of understanding mediants through the visualization of Simpson's paradox, but we have also shown that even by playing around with what may initially seem like a silly and useless concept, we can get lots of unexpected results. We managed to link together concepts that at first may not seem related to each other at all. This is part of how math discovery works, and it is a big part of what makes math beautiful. Not only did we prove a bunch of new ideas using the mediant concept we invented, we also needed to gather all kinds of mathematical concepts to prove some of these ideas. In order to show that the Stern-Brocot tree lists every rational number, we had to use a combination of linear algebra, geometry, and number theory. But in addition to rigor, we also used different visualizations to help us hone our intuition, such as using Ford circles to see which fractions satisfy 80 minus BC equals 1. We should learn to embrace this exploration and let our curiosity take us where we want. If we end up where we expected, great. If we end up somewhere completely different, that's also great. While I'm very happy to have completed a video lecture on mediants specifically, I really hope that you all take away a more important point. Don't shy away from experimentation and exploration. Don't be afraid to look somewhere new. You never know what you might discover in the process. In addition to linking some sources in the description, I want to give a big thanks to Math Master Zach, who helped with a lot of the visual intuition and proofreading in this video. I've linked his website in the description if you want to check out some of his work. If you like what I do, please consider joining my Patreon. If that's not an option, that's okay. Subscribing, hitting the like button, and sharing the video also helps my channel grow, and I want to keep it free for everyone. Thanks for all of your support, and I'll see you next time.